Hello everyone, today we will solve the question paper of Computer Oriented Numerical Method of IIPS DAVV. So let's get started. The first question is to write an algorithm or flowchart to solve the following pairs of equation for x and y given the values of a11, a12, a13, a21, a22 and a23 are given for the following cases. So the flowchart is start, input a11, a12, a13, a21, a22, a23 and then perform the forward elimination followed by back substitution and then print x1 and x2 and then stop. Now we perform the following pairs of equation by Gauss elimination method and convert the values of case 1 into augmented matrix. The augmented matrix is 2.5, 5.2, 6.2 in the place of a11, a12, a13 and 1.251, 2.605, 3.152 in the place of a21, a22 and a23. Now with the help of this augmented matrix, we convert it into diagonal matrix using operation R2 is equal to R2 minus R1, A21 upon A11. Here 2.5 is as a pivot. We get 2.5, 5.2, 6.2 in the place of A11, A12 and A13, 0, 0.00292, 0.0452 in the place of A21, A22 and A23 in diagonal matrix. Now performing forward elimination phase, we obtain the values of x1 and x2 such that x1 is equal to minus 32.79451 and x2 is equal to 16.9589. Similarly, in case 2, we will follow the same procedure as in case 1. In case 2, the augmented matrix is 2.5, 5.2, 6.2 in the place of A11, A12 and A13, 1.251, 2.606, 3.152 in the place of A21, A22 and A23. By Gauss elimination method, we perform the operation R2 is equal to R2 minus R1, A21 upon A11. Now converting the augmented matrix into diagonal matrix, we obtain 2.5, 5.2, 6.2 in the place of A11, A12 and A13 respectively, 0, 0.00392, 0.04952 in the place of A21, A22 and A23. Now performing the forward elimination phase, we obtain the values of x1 and x2 such that x1 is equal to minus 23.7959 and x2 is equal to 12.63265. Similarly, in case 3, we follow the same procedure as above. The above matrix is written in augmented form. The augmented matrix is 0.2 e minus 4, 2.0, 2.0 in the place of a11, a12 and a13 respectively, and 1, 2 and 4 in the place of a21, a22 and a23. Performing Gauss elimination method, we follow the procedure R2 is equal to R2 minus R1, A21 upon A11. The diagonal matrix is 0.0002, 2.000, 2.0 in the place of A11, A12, A13 and 0, minus 99,998 and minus 99,996 in the place of A21, A22 and A23 respectively. Similarly, following the procedure, forward elimination phase is, according to forward elimination phase, the values of x1 and x2 are 2 and 0.9998 respectively. Similarly, in case 4, the augmented matrix is 1, 2, 4, 0.2 e minus 4, 2 and 2. Now converting the augmented matrix into a diagonal matrix with the help of operation R2 is equal to R2 minus R1, A21 upon A11. The diagonal matrix is 1, 2, 4, 0, 1.9996, 1.9992. Forward elimination phase gives the values of x1 and x2 respectively, where x1 is equal to 2 and x2 is equal to 0.9998. Now we have solved all the 4 cases of the question, and let's get back to the question. The first part of the question says, comment on the result of case 1 and case 2, where there is change of 0.0001 in one of its coefficient. In case 1, the values obtained of x1 and x2 were minus 32.79451 and 16.9589 respectively, and in case 2 the values were minus 23.7959 and 12.63265 respectively. Hence we can conclude that the values of A22 by changing by 0.001, then the result displays a big change in their x1 and x2 value. The second part of the question is how interchange of equation affect the solution in case 3 and case 4. In case 3 the values were 2 and 0.9998 respectively, and in case 4 the values were 2 and 0.99998 respectively. Hence we can conclude that the interchange of equation does not affect the solution of case 3 and case 4. The second question is, consider the quadratic equation x square plus 2x minus 2 is equal to 0 to obtain the root in floating point with 4 digits in mantissa. Substitute the root in equation. Comment on the satisfiability in both the cases of x1 and x2. The given equation is x square plus 2x minus 2 is equal to 0. Finding the roots of this equation using Newton Raphson method, we have to also find the differential of the function, that is 2x plus 2. Now substituting 0 in the equation, we obtain minus 2, that is the value is negative. If we substitute 1 in the function, we get answer 1, that is positive. So the first root must lie between 0 and 1. Similarly, the second root should lie between minus 3 and minus 4. We know m is equals to b minus f of b upon f dash b for Newton Raphson method, such that it is the iterative method to find the root in Newton Raphson method. For roots between 0 and 1, we have written a table below such that its first iteration is b is equal to 1, m is equal to 0.75 and fm is equal to 0.0625, such that in third equation we got the root such that m is equal to 0.7320 and the second root must lie between minus 3 and minus 4, such that in 3 iterations we also get the value of second root, which is minus 2.732051. Instead of finding roots manually, we can also find a root using a C++ program. So let us see a C++ program. Here is the code for given question. Compiling the code and then running. First, the value of b is 1.000 and the value of e is 0.0001. So here we get the root in 3 iterations. Also, if we put minus 3 as value, we obtain another root such that m is equal to minus 2.732051 in 3 iterations. I have provided the code to obtain the root of given question from Newton Raphson method in the description of this video. Now let us go back to our question. Since now both the roots of the quadratic equations are obtained, now substituting the root in case 1 and case 2 equations. Case 1 equation is x square plus 2x in bracket minus 2. Substituting root is equal to 0.7320 in the equation, we get x1 is equal to minus 0.000176. Similarly, substituting another root in the same equation, which gives x2 is equal to minus 0.00176. In case 2, the order of the elements are reversed. The equation is 2x minus 2 in bracket plus x square. Substituting 0.73205 in equation, we get x1 is equal to minus 0.5 times 0, 279. And now again substituting minus 2.73205, which is another root of the equation, in the given equation, which gives x2 is equal to minus 0.5 times 0, 279. Now we have substituted both the roots in both the cases, and we can conclude that answer of both the cases are different. Now let us go back to third question. Third question says that how are polynomials represented in computer? Also write an algorithm or flowchart to evaluate polynomial. In computer, polynomials are represented by many ways. First is array, and another is linked list. For example, if a polynomial is x to the power 6 minus x, and we have to store this polynomial in computer, then in array it will be stored as shown in figure. The another example is linked list. In linked list, the example is 10x square plus 5x square plus 20x plus 3, which stores the polynomial in the form as described in the figure. In array, as we can see, there are many spaces which are empty. Hence, it occupies more spaces than linked list. Hence, a linked list are more preferred to store the polynomials in computer. Here is now an algorithm to evaluate the polynomial. The first part of the question says that compare the efforts in multiplication number and addition of brute force method with recurrence relation method. The answer of this part is evaluation of polynomial by brute force technique is simple but involve n plus 1 upon 2 multiplications and n additions. The algorithm which follows the number of multiplication is reduced to n. The algorithm is based on following alternate method of writing the expression. For example, a polynomial px is equal to a0 plus a1x plus a2x square plus dash 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 an x to the power n. Now, taking x common from the second term, we get a0 plus x, a1 plus a2x plus dash 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 an x to the power n minus 1, and so on. Now, the second part of the third question is write the recurrence relation of dividing this polynomial by x minus r. Here we consider dividing a polynomial an x to the power n plus an minus 1 x to the power n minus 1 plus dash 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 a0 by x minus r, where r is the root of the original polynomial. The division method is shown below, and also the algorithm for this division method is written below. Now let us go to the fourth question of this question paper. For question 4 says compare the iterative method of root finding with comments on reliability of convergence. Here is a table for comparison. The first column of the table is method, second is iterative formula, order of convergence, and reliability of convergence. The first method is bisection method. Here the iterative formula is m is equal to a plus b by 2 and its order of convergence is 1. In bisection method, it guarantees convergence. The second method is false position. Its iterative formula is m is equal to a f of b minus b f of a whole upon f of b minus f of a. Its order of convergence is 1, and also false position method guarantees convergence. The third method is second method. Its iterative formula is m is equal to a f of b minus b f of a whole upon f of b minus f of a, such that its order of convergence is 1.6180. It is the most economical method. It does not guarantee convergence if roots are not near. The fourth is Newton Raphson. Its iterative formula is m is equal to b minus f of b whole upon f dash b. Its order of convergence is 2. It converges very fast. It is sensitive to starting values. The fifth method is successive approximation. Its iterative formula is xi is equal to g xi minus 1. Its order of convergence is 1, and it is easy to program, hence it guarantees hence there is no guarantee of convergence. Thank you.